Okay, so it is the time. Let us continue with the atomic theory. I gave you already an introduction in the last class. So we saw that the first element theories were actually non-atomistic theories. But the atom hypothesis was actually already introduced by the ancient Greeks, but then it was forgotten for about 2,000 years and was just rediscovered by John Dalton with his atom hypothesis. So at this time, first, an atom was considered to be completely indivisible, but then the electron was discovered, and a first atom model, Thomson's atom model, was introduced, which for the first time contained a subatomic particle, and that was Thomson's atom model, and we discussed the nature of Thomson's atom model in the last class. So Thomson's atom model assumes that there is a positively charged mass, and the electrons are embedded in that atom like little raisins within a cake. So of course, any theory needs experimental verification. So what would be an experiment that could either validate Thomson's atom model or disprove it? And if Thomson's atom model is disproved, what atom model would replace, better atom model would replace this model? And Sir Ernest Rutherford designed an experiment, which is today called the gold foil experiment, which showed that Thomson's atom model is not correct. And you see actually here how this experiment is being set up. Yeah, we should probably close the door because otherwise it's too noisy. Thank you. So you see here a gold foil, which is very thin, only about 2,000 atoms thick. And that gold foil here is surrounded by photographic film. Okay. And you see here on this side a box. So that box is basically a lead box, which contains an element which is radioactive and sends out so-called alpha radiation. So alpha radiation is, as we know today, helium nuclei. So alpha radiation is basically a helium nucleus containing 2 protons and 2 neutrons. So of course, such a particle has a high mass and has a positive charge. Now, basically, these alpha particles were shot at the gold foil simply by an opening here through that lead container. And that photographic film here would basically detect what would happen with these alpha particles as they're being shot at the gold foil. So if Thomson's atom model were correct, they should actually all go straight through the gold foil. It would be like shooting with a bullet at a plum pudding, right, where the mass is homogeneously distributed, and just because the mass of the bullet would be so much more concentrated, the bullet actually should just go straight through that plum pudding. So what was observed, however, was something different. So while most of the particles actually went straight through the gold foil, a few of them, but only a few of them, got deflected, and even fewer of them were reflected. Okay? And that meant that Thomson's atom model actually couldn't be correct. If it was correct, really all the alpha particles would need to go straight through. Therefore, what other atom model would be consistent with the experimental observation? And the basic conclusion that Rutherford drew was that the atom must be essentially empty space, with a small, heavy, positively charged nucleus. Okay, so whenever the alpha particles would actually hit that very small nucleus, the alpha particles would be reflected. Okay, of course, these would be only few. If they passed relatively close by, they would be deflected because the alpha particle, as well as the nucleus, would have the same charge, positive charge. But most of the alpha particle would just go straight through just because the atom would be mostly empty space, and the electrons would be located as small particles within that otherwise empty space. Okay, but because the electrons would have a much smaller mass than the nucleus, the path of the alpha particles would not be influenced by the electrons. So by analyzing the intensity ratio between the non-deflected alpha particles and the reflected particles, Rutherford was able to calculate what would be actually the ratio between the radius ratio between the nucleus and the overall atom. And he calculated that, well, the atom, the radius of the atom, overall atom, would be about 10,000 times larger than the radius of the nucleus itself. So the question was, of course, why would the atom be mostly empty space? How could one explain that? And Rutherford assumed, well, the atom would be mostly empty space because the electrons would be in motion, okay? And they would circulate in orbits around the nucleus, whereby arbitrary radii would be allowed. That means that very small radii would be possible, very large radii would be possible, but there would no be discrete radii allowed. So with this model, one could explain why the atom wouldn't be collapsed, okay, which would be a result of the electrostatic attraction between the electrons and the nucleus. Okay, so what would hold the electron stable in orbit would be nothing else but the centrifugal force, okay, associated with the motion, which would be equal to the electrostatic force by which the electron would be attracted to the nucleus. So assuming that those would be opposite but otherwise equal, the stability of the electrons in the orbit would be explained. All right, so there is, however, a significant problem associated with this simple picture, which is that an electron in an orbit, because the electron is a charged particle, is actually constantly accelerating charged particle according to the laws of classical physics. And because of that, the electron should constantly send out electromagnetic radiation. However, such radiation was never experimentally observed. And secondly, because the even if the electron sent out electromagnetic radiation constantly, the electron would lose energy constantly, okay? And because of that, it could actually not be stable in the orbit, okay? Rather, it would actually spiral down, yeah? And the orbit would over the time become smaller and smaller, and the atom would eventually collapse. However, that's also not experimentally observed. Atoms are actually pretty stable, and they don't just collapse. So that meant that this atomic model, while maybe a step forward, still doesn't correctly reflect the reality, and still couldn't be the final atom model. And as we know today, the Rutherford atom model is not the final atom model. So now, what better atom model could be developed that would actually address the shortcomings of the Rutherford atom model? And Niels Bohr thought about that, and he came up with an improved atom model, which is now named after him. And this atom model is called the Bohr atom model. Okay. So now, what inspired Bohr's atom model? And these are actually two developments in the field of physics that happened at the time. And these were, firstly, the explanation of Blackbody radiation by the assumption of the quantization of energy. And that was an idea introduced by Max Planck. So first of all, let us analyze what is meant by Blackbody radiation. So Blackbody radiation is the electromagnetic radiation everybody sends out due to its temperature. Okay? And the wavelength and the intensity of that radiation depends on the temperature. Okay? So generally, the higher you heat a black body, the higher the intensity of the black body radiation, and the shorter the wavelength. Okay? Whereby the wavelengths follow a distribution curve. And you see here a number of distribution curves for different temperatures. Okay? So you see here, for instance, at 3000 kelvins, you see there's a distribution of wavelength whereby the maximum is at approximately 1 micrometer. So this radiation is still mostly in the infrared, okay? But some of the radiation, this part here, is actually already in the visible, okay? So you know that the visible light that has the longest wavelength is red light. Okay? Therefore, when you actually heat a body, it first glows red. Okay? Okay? It actually glows before that, but you can't see that electric radiation because the wavelength is too long. Okay, we are on the IR, and at even lower temperatures, we are even in the microwave region. All right, but now as we go to higher temperatures, so here's another example, 4000 Kelvin, you see that the intensity of the emitted radiation increases, but also the maximum shifts, and it shifts towards smaller wavelengths. So now we see that a greater fraction of the emitted radiation is already in the visible region. Okay? So for that reason, at higher temperature, the color of your object shifts from red more to orange as other colors start to mix into the red. Okay? And now if you go to even higher temperatures, well, the intensity of the radiation increases, but the maximum shifts further to smaller wavelengths. All right? And at these temperatures, then you also have a significant amount of UV radiation in your mix as well. Okay? So if you go to extremely high temperatures, right, you will see that your object starts glowing white. Okay? But you already have a significant amount then of UV radiation as well. So this phenomenon of the black body radiation, and especially these distribution curves, need an explanation and, well, a proper mathematical description. Okay, and classical theories could not adequately describe these curves. Okay, rather than that, classical theories available at this time predicted what is called the so-called UV catastrophe. This is this curve here. Yeah. So I would actually say that, well, the intensity would continuously increase at decreasing wavelengths, and continuously so. Okay, so the curve would actually not go through a maximum, but would continuously increase. And that would mean that basically any object at any temperature would glow white hot. And that's just not experimentally observed. So now Max Planck made an assumption, which was that energy would be quantized, and with the help of the quantization of energy, one could basically develop an equation that would fit these curves here correctly. All right. So at that time, he had no good reasoning as to why energy would be quantized, but he used the argument in order to fit the data. Okay. So the quantization, the assumption of the quantization of the energy led to this famous equation here. E is equal to m times h times nu. Okay. And this equation reflects the quantization of energy. So it says that we have electromagnetic radiation, which has a particular frequency mu, then its energy can only be an integer number of that frequency times a proportionality constant, which is now named after Max Planck, the Planck constant. Okay, so we could either have 1 times this quantum h times nu, 2 times, 3 times, 4 times, 5 times, an integer number of times, but not something in between. Okay. So now with the help of the assumption that energy was quantized, he could develop another equation. This is called the Planck equation. And you see this equation here. And you do not have to memorize this equation. And this equation now adequately describes the intensities of the black body, okay, the intensity of the black body radiation as a function of the wavelength at a given temperature. Okay, so equation matches experimental observation well, which means that equation is probably right. Okay, that also means that the assumption that energy is being quantized is likely right. We just do not know actually why at this point. Okay. So now with this, for the first time, actually, the idea of quantization appeared, and it appeared again when an explanation for the absorption and emission spectra of atoms needed to be found. Okay, so atoms, as it was found, could actually absorb and emit electromagnetic radiation, but if they do, they only absorb or emit electromagnetic radiation of very discrete frequencies. And which frequencies could be absorbed or emitted would depend on the atom type. Okay, so here, for instance, you see the absorption or the emission in the emission spectrum of the hydrogen, and you see that in the visible there are actually 4 discrete lines, yeah? Associated with 4 discrete frequencies of wavelengths the hydrogen atom can absorb, and after absorption it can also re-emit again. So that was an experimental observation, and the frequency series in the visible is named after its discoverer, the Balmer series. Okay, so after that, it was also discovered by Paschen and Lyman that the hydrogen could also absorb in the IR region, but again only discrete frequencies, and also in the UV region, again only discrete frequencies. Okay, that would be called the Paschen series and the Lyman series, respectively. So of course, the question was, well, is there a mathematical relationship between these frequencies and the associated energies? And if so, what's that relationship? Can one cast that into a formula? And the answer is, for the hydrogen, that's straightforward. For the other elements, it's actually not. But for the hydrogen, we can develop a very simple formula, and that formula is here, which says that, well, the energy differences between associated with these different lines is equal to a constant. It's named the Rydberg constant times 1 of an integer number square minus 1 over another integer number square, whereby the first integer number would be smaller than the second integer number. Okay, so it appeared that well, the absorption and emission spectra of hydrogen could be explained by integer numbers, and another name for integer number is today a quantum number. Okay, so that leads to the idea that maybe the atomic structure had to do with integer number, and if energy was quantized and the atomic absorption and emission spectra were quantized, okay, maybe also the energy of an electron in a hydrogen atom was quantized. Okay, so that would mean that, in contrast what Rutherford assumed, the electrons could not move around the nucleus of a hydrogen atom in arbitrary orbits, rather than that only discrete orbits would be allowed that would be associated with discrete radii. And these orbits would then be associated with discrete energies. Okay? And because only discrete energies were allowed, okay, the energy differences between these orbits would also be quantized. All right? So Bohr overall developed 4 postulates, which you see here. So he said that, like in the Rutherford atom model, an electron in an atom moves in a circular orbit about the nucleus under the influence of Coulomb attraction between the electron and the nucleus, obeying the law of classical mechanics. Okay. However, instead of an infinity of orbits, which would be possible in classical mechanics, it's only possible for an electron to move in an orbit for which its angular momentum, L, is an integral multiple of h over 2 pi, which would be consistent with the quantization of energy. Okay, so now it's because of that quantization. Okay, it's because of the quantization that the electron would not behave like a classical particle in an orbit and not constantly send out electromagnetic radiation, and because of that would be stable in the orbit. Okay, so it could only actually emit radiation Okay, if it actually jumps from a higher orbit to a lower orbit, okay, and it could absorb electromagnetic radiation when it actually jumps from a lower orbit to a higher orbit. And this would explain the quantization of the absorption and the emission spectrum. Okay, so this is basically stated here in postulate 4. All right. So now this is the qualitative picture. Now, can we actually calculate the radii of the electrons in the orbits for a hydrogen atom? Can we actually calculate the energies, and can we actually show that the energy difference between these electron energies is what is experimentally measured via the absorption and the emission spectrum? Okay, so if we can do this, this would of course much validate this atom model, which is called the Bohr atom model. All right, now I wanted to briefly show you that this can be done by some simple algebra. Okay, so let's first calculate the radii of the electron in the orbit of the hydrogen atom. So we are making two assumptions here, which the first one here is basically consistent with Bohr's first postulate, which says that the centrifugal force is equal to the Coulomb force. So according to classical mechanics, the centrifugal force is the mass times the velocity square over the radius. Okay, whereby in this case the mass is the mass of the electron, okay, and the velocity is the velocity of the electron in the orbit. Okay, r is the radius of the orbit. Okay, that would need to be equal to the Coulomb force, and the Coulomb force would be the force between one proton and one electron. Okay, which is given by this formula here. So that's the elementary charge square over 4 pi times the dielectric constant of the vacuum times the radius square. All right. So basically, this assumption is taken from Rutherford. Now, the second assumption now introduces the quantization of the electron. Okay? It says that the angular momentum of the electron is an integer number times the Planck constant. So it's 2 times pi times r times m times v, okay, which is equal to n times h. So now one can mathematically solve this equation for the velocity, and then the velocity is equal to n times h over 2 pi r times m, okay, whereby m is again the mass of the electron. And then one can substitute v in this term here by this term. So we introduce this term for v in here. Okay, and then the left side of this equation becomes m times n squared times h squared times 4 pi squared times r to the power of 3 times m squared. So the right side of the equation remains, saying we haven't done anything with it. Okay, so now all we need to do is basically solving this equation here for the radius. Okay, so now let's do this. So this is just the same equation as you've seen on the previous slide. What we can do is multiply this equation of 4 pi times epsilon 0 r squared. Okay, so that brings this term here on the left side. Okay, so then the left side becomes n squared times h squared times epsilon 0 over pi rm. Okay, The right side here is reduced to E square. So now we can divide by E square and multiply by R. Okay, so this brings R here to the right side and E square to the left side. That means that we basically solved this equation now for R. Okay? And then R is n squared times h squared times epsilon 0 over pi me squared. So this is now our first result. So when we analyze this result, we notice that the radii, the allowed radii for the electron, is only depending on the quantum number n. Precisely, it's a function of the square of the quantum number n, just an integer number. So all the other variables here, they're actually constants. So the Planck constant is a constant, the dielectric constant of the vacuum is a constant, pi is a constant, the mass of the electron is a constant, and the elementary charge is also a constant. So basically, the radius is a constant times n squared. Okay? So now we can just insert different numbers for n, starting with 1, and that will allow us to actually calculate the absolute values for the allowed radii. So let's do this just for n equal to 1. So n would be 1, then there would be, well, 1 squared times h squared times epsilon 0 over pi me squared, and that would give just 5.29 times 10 to the minus 11 meters. Okay, we've seen that by simple algebraic calculation, we can calculate the radius of the first radius of the electron in the hydrogen atom. And we could calculate all the other allowed radii by just inserting other quantum numbers here. Okay, the next one would be 2, then there would be 3, then there would be 4. And the radii would correspond then to the second allowed radius, the third, and the fourth, so on. Okay. Sorry. So now, what would be the associated energies? So we would assume that these energies are now a function of these radii. Okay, how can we show that? So now let us just first assume that generally the energy of a particle is the sum of its potential energy, yeah, plus its kinetic energy. So our task is to calculate the kinetic and the potential energies separately and then add them together. So we can start with the kinetic energy. The kinetic energy of a moving particle is given by the formula 1/2 mv squared. Okay. So now we know from our previous equation 1 that mv squared over r is e squared over 4 pi epsilon 0 r squared. So what we can mathematically do is we solve this equation here for v squared, and then v squared is equal to e squared over 4 pi epsilon 0 rm. Okay, and why do we do this? Because now we can actually insert this term here into that equation over there, substitute v squared by this term. Okay, and then the kinetic energy is overall e squared over 4 pi epsilon 0 r. All right, now what is the potential energy? Now the potential energy is basically the Coulomb energy between the attractive Coulomb energy between the electron and the proton. Because that is an attractive energy, this energy, as you can see here, is negative. Okay, you can understand this the following way: when you have a proton and you have a free electron, and you add the free electron to the proton to make a hydrogen atom, then this is an exothermic process. Yeah, so this is another way how we can understand this negative algebraic sign. So the potential energy is minus E square over 4 pi epsilon 0 r. All right. So now we can just basically add these two. So the overall energy is the kinetic energy, which is this one, plus the potential energy, which is this. You see here again the kinetic energy. See here the potential energy. Okay. You see they are mathematically similar. So this is E squared over 8 pi epsilon 0 r, and that is E squared over 4 pi epsilon 0 r. So we can factor out E squared over pi epsilon 0 r. Okay. And that factor is then multiplied with 1/8, okay, minus a quarter, 1 over 4. Okay. So 1/8 minus a quarter, well, that is just minus 1/8. Okay, so therefore the result is minus E squared over 8 pi epsilon 0 r. Okay, so you see that this energy is overall a negative energy. Okay, and that is again because it's a binding energy. It can be understood as a binding energy. Okay, so now you see that the radius r appears here in our result. And we have previously seen that the radii are quantized, and we have the mathematical expression for the radius as the function of the quantum number n. So we therefore can insert this term here for r. So we insert this over here, and then the mathematical expression becomes E is equal to minus e to the power 4m over 8 epsilon 0 square n square h square. So now let us analyze this result again. We again see that also the energy is only a function of the quantum number n. So everything else in this equation here is just a constant. So again, the elementary charge is just a constant. The mass is just a constant. Well, 8 is just a constant. The dielectric constant of the vacuum is just a constant. And the Planck constant is also a constant. So overall, the energy, allowed energies of the electrons are a function of 1 over n squared multiplied with a constant. Okay. So now, knowing the energies of the electrons, we can now also calculate the energy differences of the electron in different orbits. Okay. So this is just the equation that we have previously calculated. So now, when we have energy differences between two orbits, okay, then we have a delta E, okay, and that would be, well, e to the power 4 times m over 8 epsilon 0 square n high square h square. So that would just be a higher quantum number associated with a higher orbit minus basically the same term but with a lower quantum number n square. Okay, so that would then be, well, e to the power 4m over 8 epsilon 0 square h square times 1 over n low square minus 1 over n high square. Okay, so when you look at this formula, then you see that there's a striking difference with the Rutherford formula, which was previously empirically found when analyzing the hydrogen absorption and emission spectrum. So we can compare now the theoretically derived formula with the empirically found formula. Okay. So now empirically, we found this formula here, and you see that this part and that part is exactly identical. Here we had the empirically found Rutherford constant, RH, okay, and here we had this theoretically derived constant. Okay. So now one can just explicitly calculate the value of that constant Okay, just by multiplying and dividing all these individual constants with each other, we'll find, well, that this here matches exactly that. So RH is actually exactly e to the power 4m over 8 epsilon 0 square h squared. And that means that experiment in theory are an excellent agreement, which of course strongly supports the Bohr atom model. And it of course strongly supports that the radii of the electron in the orbits are really being quantized. Okay? And there's a reality to the quantization of the electron in the hydrogen atom. Okay. So this was of course another huge step forward, but still it left a number of questions open. Okay. So the first problem, which is still with Bohr's atom model, is that it can only explain the hydrogen spectrum. It fails to explain all the other spectra of all the other elements, which is, of course, a severe limitation. So this indicates, while there is certainly a piece of truth in this atom model, but it still cannot be the final answer, because only in a very special case, experiment and theory are in agreement. In the case of all other atoms, they're still disagreement. Okay. So now, why could this be? And that leads actually to the second problem, which is that Bohr's postulates are ad hoc and they lack an explanation. So in particular, it doesn't really explain why the electron would behave the way it behaves. Okay, why does it act as a quantum mechanical particle, being allowed only in certain orbits and not on all orbits? Okay, so there's a lack of an explanation as to what causes the quantization of the orbits of the electron in the hydrogen atom. And the answer is that we have not considered an important property of the electron yet, which is the wave-particle dualism of the electron. So an electron doesn't only have particle properties. As we will see, an electron also has wave properties, and only when we account for both the particle and the wave properties, then we can properly describe the electron, and then the problems associated with the Bohr atom model will go away. Okay. So now, therefore, we need to look more closely as to why an electron has not only particle properties, but also wave properties. So the wave-particle dualism is actually universal. It doesn't only hold for electrons, it holds for all particles. And originally, it was actually discovered for the electromagnetic radiation itself, which in the classical view is not associated with the particle at all. Okay? But it was discovered that also electromagnetic radiation has this wave-particle dualism, and the particle associated with electromagnetic radiation is actually the photon. So let us see how the wave-particle dualism for electromagnetic radiation was actually discovered. All right, so it was discovered in the context of the explanation for the photoelectric effect. So the photoelectric effect occurs when you shine electromagnetic radiation on a metal surface. So what you will find is that when your electromagnetic radiation is actually below a certain threshold frequency, just nothing happens. But all of a sudden, above a certain threshold frequency, the electromagnetic radiation is able to eject electrons from the metal surface. And these electrons have a certain kinetic energy. Okay, so now what is the explanation for this photoelectric effect? And Albert Einstein analyzed the photoelectric effect, and he actually won the Nobel Prize for the explanation of it. So he just analyzed the kinetic energy as a function of the frequency, the kinetic energy of the electron as a function of the frequency of the incident radiation. And we found that there's a linear relationship. Okay, so below the threshold frequency, where the kinetic energy of the electrons is zero, just because no electrons are being ejected, but above that threshold frequency, there's a linear relationship. Okay, so now he just analyzed the slope of this line and found that the slope of this line is identical to the Planck constant, which Planck previously introduced when he assumed that energy was being quantized. Okay, and so the kinetic energy of these electrons could be described by, well, h times nu of the incoming electromagnetic radiation, which would represent the energy of the incoming electromagnetic radiation, minus a binding energy, the energy by which the electrons would be pulled to the metal surface. Okay, so basically the electromagnetic radiation would need to overcome this binding energy so that the electron could be ejected. So now the most straightforward interpretation of this is to assume that the electromagnetic radiation is associated with a particle. And because it's associated with a particle, the quantization of the electromagnetic radiation or its energy is explained. Okay, because particles can only come in integer numbers. Okay, so assuming that electromagnetic radiation is quantized and comes in discrete quantities, this could most satisfactorily be explained by the fact, well, there's a particle associated with that electromagnetic radiation. All right, and they could only come in integer numbers. Okay, so now in this picture, basically, the particle associated with the electromagnetic radiation, which we call photon, okay, would hit the electron. Okay, if the energy of the photon, which would only depend on its frequency and not on the intensity of the radiation, would be large enough, then that electron could be ejected. Okay, and the kinetic energy would be nothing else but the difference between the energy of the electromagnetic radiation and the binding energy of the electrons in the particle. Okay, so one can also describe this mathematically fairly easily and illustrate the wave particle dualism of the photon mathematically fairly easily. Again, starting out from Planck's equation and taking to the consideration Einstein's equation, E is mc squared. So this equation says that basically mass can be converted into energy which is electromagnetic radiation. And because of that, one could set these two equations equal so that mc squared would be equal to h times mu. And then the only remaining task would be to solve the equation for mu, which would be then mc squared over h. And one could substitute the frequency also by lambda, and then the wavelength of the electromagnetic radiation would be h over mc. So now you see that there are actually wave properties and particle properties being correlated. Yeah. So a frequency or a wavelength, that's certainly a wave property. Okay? But a momentum, which would be the product of mc, that would be actually particle property. Okay? Also, the mass would be typically particle property. And you see that there are even relationships. So basically, the longer the wavelength, the smaller the particle, yeah, and the smaller the mass of the particle, and the larger the mass of the particle, the smaller the wavelength of the electromagnetic waves. And that would basically make understandable why, well, a shorter wavelength would be associated with a higher energy, okay? Because the mass of the particle would increase, and when you imagine a collision of a photon having a larger mass with an electron, that larger mass would more easily eject that electron from the particle, okay? From the matter. All right. So this is the wave particle dualism of the electromagnetic radiation. So in the next class, we will make the transition from the photon to the electron, and then get back to what is called the wave mechanical atom model, which is the final atom model as we know it today. And with that, we can stop.